Hi everybody, welcome to a Physics Fundamentals screencast. This particular screencast is going to focus on using Newton's second law to do calculations for single objects. I'll have a second screencast that will look at how to do Newton's second law calculations when you have systems of objects. All right, so that single object is exactly what it sounds like. One object with forces acting on it. All right, so there are two ways to determine F net. All right, the first way is to take the free body force diagram, look at all the forces that are acting on the object, find the unbalanced forces, and add them together. All right, so F net can be equal to force 1 plus force 2 plus force 3, etc., etc. All right. The second way to find F net is to use Newton's second law, which says the net forces acting on any object must be equal to the mass of that object times its acceleration. All right. Now, acceleration is not going to be due to gravity in all of these cases because we're talking about how the object is moving, and it's not always due to gravity's pull. All right, so let's talk just a little bit about this equation and the relationships. So we have F net equal to mass times acceleration. All right, so if we look at the relationship between force and mass, it's reasonable to assume that as the mass of an object increases, the force required to make it move or to change its motion is also going to need to increase. So this is going to be a direct relationship. I mean, think about pushing a car versus trying to push a tricycle, right? It's going to be a lot easier to push the tricycle. You won't need as much force to make it move because it has less mass, all right? We can also look at the relationship between F net, the net force, and acceleration. All right, so it also is reasonable that if you apply more and more force to the same mass, you're going to see its acceleration value go up and up and up. So again, this is a direct relationship between these two variables. All right, and then finally, we can look at the relationship between mass and acceleration. If you can only apply a certain amount of force, then the more mass you have, the less acceleration you're going to see. And then vice versa. If you apply the same amount of force to an object that has less mass, you're going to see a higher degree of acceleration. So these are inversely related to each other or indirectly related. All right. Now, as we start to work these problems, I want to remind you, all right, about listing your variables, your formulas, substituting in, and then solving for your answer. All right. And as always, units are important. Okay. All right. So let's look at some problems. All right. So you push a 50-kilogram box across a rough floor with a force of 500 newtons at constant velocity. Draw the free body force diagram of all the forces acting on the box, label the forces, and include numerical values. Okay, so here's our box. All right, I know that working vertically downward, I have a force due to gravity, and opposing it, I have the normal force. All right, now, because the box is only moving horizontally, these two forces must be equal and opposite. All right, I also know that I am pushing the box. All right, so I'm going to choose to be pushing to the right. All right, just so I can have a designation. So here is my applied force to the right. And because I'm moving at constant velocity, that tells me that my net force acting on this object must be 0. So my frictional force, because of that rough floor, must be equal and opposite to my applied force. So this is going to be the free body force diagram for this particular situation. All right, now it says to include numerical values, which means I must be able to figure out some of this stuff. All right, well, first, I'm given 500 newtons as my applied force. So I'm going to put 500 newtons here. And I know that the frictional force must be equal but opposite. So we're going to have 500 newtons over here. This is the negative direction and this is the positive. And we know that, but we just list the magnitude of these forces. All right, now let's think about our gravitational force and our normal force. I'm given the mass of this object, so I know that the force due to gravity is equal to the mass of that object times the acceleration of gravity. So Fg is going to be equal to 50 kilograms times 10 meters per second squared, which is going to be 500 newtons. So Fg is 500 newtons, right? And I know that the normal force must be equal but opposite, so it also must be 500 newtons. That's a lot of 500s. Okay, so that's how you can fill in some of these forces just by drawing your free body force diagram and thinking about what the information that you've been given means in terms of the forces. All right, next, part B, you need to hurry, so you accelerate the box at 0.75 meters per second squared. Assuming the friction force remains the same, what is your new applied force? Draw a new free body force diagram. Okay, so let's see. All right, so I've got my box. All right, my gravitational force and my normal force are unchanged. They're going to be equal and opposite, and they're still going to be 500 newtons each. All right, the problem also tells me that my frictional force remains the same. All right, so it must also still be 500 newtons. All right, what must have changed here is my applied force. It has to have increased. All right, how do I know that it increased? I've accelerated. All right, so that means that F net can no longer be zero. All right, so that means that I've got some sort of changing velocity, and that indicates that we've got some acceleration. Now, the acceleration listed is positive, and the box is moving in a positive direction, so I must have increased my applied force. The question is, how do I figure out what that is? All right, I know that F net is equal to that applied force plus my frictional force. I also know that F net is equal to the mass times the acceleration of my object, so I can set that equal to the applied force plus the frictional force. All right, and if I look at my information, I know the acceleration, I know the mass, and I know the frictional force. So I can figure out what my new applied force is by plugging in. All right, so I have 50 kilograms times 0.75 meters per second squared. That's going to be equal to my unknown FA and adding my negative 500 newtons. All right, now the negative is because of the direction that frictional force points. All right, so do not forget the negative. Signs are very important here. All right, so I plug this into my calculator and I solve, and I find that my applied force is 537.5 newtons. All right, so as expected, if I want to speed the box up, I need to apply more force than I was before. Before, when I was moving at constant velocity, my applied force was 500 newtons. Now that I've tried to speed my box up, I need to add in a little bit more applied force, so it goes up, in this case, to 537 newtons. Okay, all right, let's look at the next part. The box velocity at the beginning of the acceleration was 8 meters per second. What was the velocity after 8 seconds of acceleration? All right, so let's see what we know. All right, we know our initial velocity was 8 meters per second. We're asked to find our final. Our acceleration was 0.75 meters per second squared, and we're going to accelerate it over a time period of 8 seconds. All right, so I'm going to use my final velocity formula, where that final velocity is equal to the initial velocity plus acceleration times time. So that's going to be equal to 8 meters per second plus 0.75 meters per second squared, times 8 seconds. We plug all that in, and we find that the final velocity of the box is 12 meters per second after these 8 seconds. So the box has sped up, which is what I would expect. All right, and then finally, how far have you moved the box during this time? All right, so we're going to have the same variable list with the addition of B final, and we're asked to find the change in position. Now, there are a couple different formulas that you can use. My favorite is change in position is the average velocity times time. All right, so I have my change in position equal to my average velocity, which is 12 meters per second plus 8 meters per second divided by 2 times my 8 seconds. All right, so 12 plus 8 is 20, divided by 2 is 10, times 8. So I have moved the box 80 meters during this 8-second time period. Okay, so this is just an example of how we can use Newton's second law to find some of our initial information, which we then use to find velocity, time, change in position, and all of those variables we've been working with. All right, let's try one more together. All right, this one, we have a helicopter, all right, that accelerates vertically from rest to a final velocity of 25 meters per second over 10 seconds. So the first question is, what is the acceleration? All right, so we list what we know. We have V initial, V final, acceleration, time, and we have mass. All right, so from rest, so my initial velocity is 0. Our final is 25 meters per second. And we do this over 10 seconds, and I have a 750 kilogram massed helicopter. All right, so I'm asked to find acceleration first. So I look at my formulas, and my best bet is acceleration is V final minus initial velocity divided by time. So I plug those values in. So 25 meters per second minus 0 divided by 10 seconds. So my acceleration value is 2.5 meters per second squared. All right. Next, well, what was the net force acting on the helicopter? Now, I don't have a free body force diagram, so I can't do sums of forces here, but I do know the mass and I do know the acceleration. So mass is 750 kilograms. I just found the acceleration to be 2.5 meters per second squared. And with those and Newton's second law, I can figure out what that net force is. All right. So that law tells us F net is equal to the mass times the acceleration. So we plug in 750 kilograms and 2.5 meters per second squared. And the net force acting on this helicopter as it's accelerating is 1,875 newtons. All right. So for our final part, what is the thrust, which is the applied force of the rotor blades that propel the helicopter upwards? Draw a free body force diagram and label all forces, including numerical values. Okay? All right, so here's our helicopter. All right, now we know there's applied force up. All right, this is our thrust. All right, we're going to assume just for ease that there is no air resistance pushing down on the helicopter. All right, but we do have a gravitational force pushing down, or pulling down rather, on our helicopter. It's a little less than our applied force, and I know that because the helicopter is accelerating upwards, so they can't be equal to each other. The forces are not balanced here. All right. So I know that the net force is equal to the sum of those two forces, the applied force plus the gravitational force. And I have that value. So if this is my unknown, then there must be a way to find Fg, all right? And I know that the gravitational force is equal to the mass of the object times the acceleration due to gravity. And since I know the mass is 750 kilograms, and I know acceleration due to gravity is 10 meters per second squared, I know that the force due to gravity that's pulling on the helicopter is 7,500 newtons. All right, so I can plug that into my F net equation, plug in F net that I found in part B, and solve. All right, so I have 1,875 newtons as my net force, an unknown applied force, and then a negative 7,500 newtons for that gravitational pull down. All right, remember the negative sign's got to go in there because that force is pointed down. All right, so I'm going to end up adding 7,500 to both sides, and my applied force by the engines is 9,375 newtons. Okay, so this problem was a little bit different than the first one in that it gave us variables like velocity, time, and distance and asked us to work our way to F net and then to one of the forces in our free body diagrams. Okay, so if you have any questions, please let me know, and I hope you have fun with Newton's second law.